Good evening, everyone. Please join me in welcoming Dr. Anand sir, who will be guiding us through today's session. Let's give him a warm welcome. Thank you, sir, for.
Yeah, thank you, madam. So let's start. First, I'll share my screen. Is this visible?
Yeah, yes.
Okay. So let me first ask you, are there any doubts from the last lecture? Do you have any doubts from the last lecture? If you have, yes, we'll start with those. Okay. If not, let's start with something new today. So yesterday we discussed groups. Today we'll discuss subgroups. Can somebody tell me what a subgroup is?
A non-empty set of a group G, H is said to be a subgroup of G if it forms a group on the binary operations for G itself.
Right. So we'll start with let G be a group. Um, a non-empty subset H of G is said to be a subgroup of G if you start with the binary operation which we defined on G, restrict that to H, technically H cross H. This is a function from H cross H to G. This should land inside H and this operation should make H into a group. Okay, nothing complicated. It's just that subgroup which is a group. I mean subset which is a group. The only technical thing over there is the operation should be the same. So yesterday we discussed some uh, examples of groups. So one of them was Z. So can somebody tell me subgroups of Z? Some subgroups of Z?
2Z.
Yes. So let me tell you the notation. The notation is this, but usually it's denoted the other way. So 2Z is a subgroup of Z, which means if you take all the subset of all even integers, that forms a subgroup of Z. You can check that even integers are non-empty, of course, because 0 is there. And you can check that under addition, restricted from Z, 2Z forms a group by itself. Right? It's closed. Sum of two even numbers is even, and negative of an even number is even again. And 0, of course, the identity is also in 2Z. What about other subgroups of Z?
3Z, 4Z, 5Z.
Yeah.
The
So
AMZ.
more, yes. So more generally, NZ, which is all integers divisible by a fixed integer n, this forms a subgroup of Z. For every n in Z. Okay. Next example. So if you start with Z mod nz, which is Zn, what are some subgroups of Zn? N is an integer. What are some subgroups of Zn? No answer? Am I audible? Is there some network issue?
Yes, sir. Yeah, audible.
Okay, yeah. So, turns out ZD is a subgroup of Zn if D divides N. Okay? ZD is a subgroup of Zn if D divides N. But more, you can say something more. For every divisor D of N, there exists a unique subgroup isomorphic to ZD of Zn. Okay? One can check this just by starting with a generator of Zn and then raising it to the power n by d. That would give you a copy of ZD inside Zn. Okay? So now can somebody tell me the number of subgroups of Zn? What is this answer?
So phi of
Is a
n?
question. Uh-huh.
Phi of n?
No.
So
Like
tau
the
of
For
number
n.
of
example,
positive divisors of n.
yeah, exactly. Number of positive divisors of n, but what's the formula?
So first of all, we factorize the number and then we'll
Tau
add
n,
the
I think.
power all the natural number.
Yeah, so you start with n equals product over primes. P dividing n. You have p power alpha p, right? So this is the factorization of n. Now what? Now how do you find the number of subgroups using this factorization?
So then we add 1 to the power alpha p plus
Mhm.
1.
Yeah, and
And then
And
we'll
product the
yes, take the product. So the number of subgroups is equal to product of primes, product over primes p dividing n alpha p plus 1. Is this clear? Because any divisor of n uh, also has a factorization of this kind, where instead of alpha p, you'll have some integer as a power of p between 0 and alpha p. Those are alpha p plus 1 integers, and then you have to take the product of all of those. So that's the proof. Okay, so now let's move on to some non-abelian groups. Sn. What are some subgroups of Sn?
An.
Yes, subgroups of Sn. Uh, so there's a huge list, but one of them is An. So what is An?
Set of all even permutation.
Yes. So An is a set of all even permutations. So what happens over here is every element of Sn can be written as a product of disjoint cycles, but one can do better. Every element of Sn can be written as a product of two cycles. They won't be disjoint anymore, but every element of Sn can be written as a product of two cycles. They are called transpositions. Now what you do is start with any element inside Sn take its decomposition into transpositions, 2 cycles, and count the number of 2 cycles appearing over there. If that number is even, your element lies in A. If that number is odd, your element doesn't lie in A. That's how. Uh, that's the concept of even or odd permutations. Subgroups of Sn, An is one of them. What about others? So Sm for m between 1 and n. Is this a subgroup of Sn?
Yes, sir.
Why?
Because SM itself a group and it is a subset of SN.
But how do you see Sm as a subset or subgroup of Sn?
Because M is less than equal to N and SN contains a permutation of N elements and SM contains permutation of M elements.
Yes. So a copy of Sm inside Sn is all functions which fix the remaining elements. So if you take all functions in Sn which fix m plus 1, m plus 2, dot 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 till n, those form a copy of Sm. Okay. Then what about Zn? Is Zn a subgroup of Sn?
No, sir.
Why not?
The operations are different and it
No.
is not also a subset.
The question is there a subgroup of Sn isomorphic to Zn? It doesn't matter what you name these as. That's the point of isomorphisms, right?
Yes, sir. Then it will be a subgroup.
How?
Because Sn have a element of order n. We can take a n cycle, then we can take the generating set of that element.
Right.
That will be
So
isomorphic.
yeah, Zn is a cyclic group having a generator which is of order n. So if you just find an element of order n inside Sn, that would give you a copy of Zn inside Sn, right? So uh, Zn is also a subgroup of Sn. So now there are some questions which appeared in the past question papers, I think. They give you some fixed value of n, like S5, and then they'll ask you, is there a copy of Z6 inside S5? Okay, is Z6 a subgroup isomorphic to a subgroup of S5? So what's the answer?
Yes.
How?
Because S5 has an element of order 6.
Yeah, what is that element?
1, 2, 3, 4, 5.
Yeah. So yesterday we saw that the order of disjoint permutations, a product of disjoint permutations, is the LCM of their orders, right? So if you start with 1, 2, 3, 4, 5, the order of this function 1, 2 times 3, 4, 5 is equal to the LCM of order of 1, 2 and the order of 3, 4, 5. The order of 1, 2 is 2. The order of 3, 4, 5 is 3. The LCM of 2 and 3 is 6. That says 1, 2, 3, 4, 5 has order 6. So if one takes the cyclic subgroup generated by this element, that subgroup is isomorphic to Z6. Okay? Yeah. Now let me give you a theorem. Every group of order n is isomorphic to a subgroup of Sn. Okay? Not just Zn, this group of order n can be any random group. It can be non-abelian, it can be abelian, it can be cyclic, it can be non-cyclic. You know for sure that that group is a subgroup of Sn. Yeah. So one way to prove this is to do the following. So start with that group of order n. Then given any little g in that group, you look at the function going from capital G to itself, uh, which is multiplication by g. Multiplication by little g. Turns out that's a bijection, and that's how you get a copy of your group of order n inside Sn. The order of Sn is n factorial, and yesterday we saw the order of a subgroup divides the order of the group. Order of the subgroup over here is n, and order of Sn is n
N
factorial.
factorial.
Yeah, so you can see n divides n factorial, so that checks out. Okay, now moving on to matrix groups. So if you start with G, L, N, F, P, let's see. What are some subgroups of GL and FP that you know?
SLNR.
Yeah, SL and FP. SL and FP is a subgroup of GL and FP. What is SL and FP?
The set of matrices whose determinant is equal to 1.
Yeah, so subset of matrices consisting of determinant whose determinant is 1. Can you tell me the order of SL and FP?
Yes, sir.
Yeah, what is it?
So p raised to the power n
Mm-hmm.
minus
Hmm.
pn minus 1,
Okay.
then close the bracket, again pn minus 2,
Yeah,
and dot 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 at the end pn minus 1 divided by p minus 1.
right. So the numerator over here is the order of GLN, but then you see that determinant takes p minus 1 values, and doing some tricks with that information, you can show that order of SL and FP is this quotient. Okay, just to remember and prove this. What are some other subgroups of of GLN? Let me tell you a few of them. BN. These are usually called as the standard Borel subgroup. This is the standard Borel subgroup. BN is a sub of GLN FP. This is the subgroup of upper triangular matrices. Okay. These are really important. Then there is a further subgroup of these denoted by Tn. These are the diagonal matrices. And somehow there's an orthogonal complement to Tn inside Bn. I'll write those here. Un is a subgroup of Bn. These are upper triangular with ones on the diagonal. Okay. What's the cardinality of Tn? What's the order of Tn? How many diagonal entries are there which you have
And
to fill?
N.
N.
Yes, n. And on each diagonal entry, how many choices are there? How many choices do you have for each diagonal entry?
P.
No, not p, right? You cannot take 0.
N minus 1 choices.
P minus 1.
P minus
You want non-zero elements coming from fp. So there are n places. Each place has p minus 1 choices. So you'll have p minus 1 power n choices, right? So that's the order of Tn. What is the order of Un? So Un consists of upper triangular matrices with ones on the diagonal. So no choices on the diagonals. Uh, on the bottom left part of the matrix, you'll have zeros. On the top right part of the matrix, you're free to choose anything, right? So again, how many places are there above the diagonal?
N into N minus 1 by 2.
Yes, and all of those have how many choices?
P minus 1.
No, p choices now. Here, any element of fp will work.
But sir, if we take 0, then it will be not be invertible.
But identity matrix has 0 above the diagonal, right? Still it's invertible.
Yes, yes, sir.
yes, sir.
Yeah. Zeros on the diagonal are an issue, but uh, zeros off the diagonal are fine as long as your matrix is upper triangular. So UN has cardinality p power n minus 1 by 2. Okay. Note that n times n minus 1 by 2 is an integer always. 2 either divides n or n minus 1. Either n is even or n minus 1 is even. So this makes sense. What about the order of Bn? It's both of these, right? On the diagonals, you're free to choose any non-zero numbers. So you have p minus 1 power n choices for diagonal elements, and above the diagonal, you have p to the power n minus 1 by 2 choices. Okay?
Yes, sir.
So here you can see that OBN, the order of Bn, is the product of order of Tn and order of Un. So yeah, this hints towards something. It turns out that Bn is what is called as a semi-direct product of these, which will show up later. Okay. Can you see how Sn is a subgroup of GLN? Doesn't matter what field you take, FP or R. Can you see this? So just say this out loud. You want to realize permutations as matrices. So what's the answer?
So we will take 2 by n matrice, 2 by n order matrices here.
2 by n. No, you need n by n. You want to realize permutations as matrices. So you use permutation matrices, right? Let me show you how. So S2 is a subgroup of Gl2. Doesn't matter what field you take. Via or as the subset consisting of the identity matrix and this matrix. Okay. One can check that this forms a subgroup of Gl2 Fp or Gl2R, and this subgroup is isomorphic to S2. S3, how do you see S3 as a subgroup of Gl3Fp? So you start with the identity matrix, then you take all the permutation matrices. So let me see if I can write those. These correspond to cyclic permutation. I mean, 3 cycles. This corresponds to the element 2, 3 or element 2, 3. Then 1, 3 will be like this. And what's remaining? 1, 2. Okay. What we do over here is we start with the identity matrix. Now, given any element of Sn, you just apply that element to the rows and columns. That's the idea. Okay.
Yes, sir.
And that's how you realize Sn as a subgroup of GLN.
Sir, could you please show how you get the other element after the identity matrices?
Yeah. Let me tell you a proof. So these are called permutation matrices. So you can just look those up and see their exact form. But the idea over here is, so start with any element of S3. So okay, first of all, start with GLN of a field. Okay, GLN of a field, doesn't matter what field it is, FP or R. You want to realize Sn as a subgroup of GLN FP. So what you do is, given any sigma inside Sn, you let sigma act on a fixed basis of the n-dimensional vector space Fp power n over Fp. Okay? This is a linear transformation. This actually gives you a linear transformation. And the matrix form of that linear transformation is the element corresponding to sigma. Is the permutation matrix associated to sigma. Okay, so let's revise this. What happened over here is you start with GL and FP. So you take Fp power n, that's a n-dimensional vector space over Fp. Now to get an element of GLN, you just need to, so elements of GLN are invertible linear transformations on Fp power n. A linear transformation is determined by what happens to basis vectors. So you fix a basis of Fp power n and let your permutations act on the basis elements. Those will give you a bijection between two bases of the same thing. And then you consider the linear transformation associated to that bijection. Okay. So, okay, maybe I'll go slowly. Let's do the 3x3 case. So suppose you start with Fp power 3. This is generated by E1, E2, E3, right? You pick a basis E1, E2, E3 of Fp power 3. Now you start with sigma equals 1, 2, 3. Then consider a map from this set E1, E2, E3 to itself given by this permutation. So E1 goes to E2, E2 goes to E3, and E3 goes back to E1. Okay, this is a set theoretic map from one basis of a vector space to a different basis of the vector space. Okay, this corresponds to a linear transformation, and that linear transformation has the matrix. Let's write down the matrix. So how does one compute the matrix associated to this linear transformation? The first column of the matrix is where E1 goes, right?
Yes, sir.
Where does E1 go? E1 goes to E2. E2 is 0, 1, 0. Then the second column is where E2 goes. E2 goes to E3, which is 0, 0, 1. And the third column is where E3 goes. E3 goes to E1, so that's 1, 0, 0. So 1, 2, 3 corresponds to this matrix 0, 0, 1, 1, 0, 0, 0, 1, 0. Is that clear?
Yes, sir.
Yes,
Okay.
sir.
That's how this matrix is obtained. Okay. Now, let me tell you one nice result. Turns out S3 is also a subgroup of Gal2. Okay. S3 is also a subgroup of Gl2. S3, which is the same as D3. I'll just talk about D3. It's easier. So how do you realize D3 as a subgroup of Gl2FP? If you had revised, you would see that there is a matrix -1, -1, 1, 0, which has order 3, and a matrix 0, 1, 1, 0, which is of order 2. D3 is generated by R and S, if you remember. So to find a copy of D3 inside Gl2FP, you send R to this matrix and you send S to this matrix. Now, go back after this lecture and check if the relation for D3 is satisfied by these two matrices. You know that S R S inverse is R inverse. So check 0, 1, 1, 0, -1, -1, 1, 0, 0, 1, 1, 0 inverse is the inverse of this matrix. Try to do this. Okay. Next, let me give you a theorem. It says that if H is a subgroup of G and G is a finite group, then the order of H divides the order of G. Okay. Just a theorem, Lagrange's theorem, that if you take a subgroup H of G, then the order of the subgroup divides the order of the group. There's one necessary condition to get subgroups. We saw above that for cyclic groups, you have some kind of a converse to this theorem, that for every divisor of the order of G, you get a unique subgroup. But in general, the converse of this theorem is not true. Does anybody know a counter example to the converse of this theorem?
Yes, sir.
Yeah, what is the answer?
So it's a Klein's 4 group having order 4, but there is
Yeah, but there is
Sir, A6.
A6. What's the subgroup of A6? The answer is in A4. A4 does not have a subgroup of order 6. Okay. Yeah. So this theorem has some nice consequences. Let me tell you some of them. As we saw, Sn is a subgroup of GL and FP, right? SLN is a subgroup of GLN FP. That implies the order of SN divides the order of GLN. This means n factorial divides p to the n minus p to the n minus 1 times p to the n minus 1. Okay, there's one thing. Then S3 is a subgroup of GL2. That implies 6 divides p square minus p times p square minus 1. So yeah, you have some nice kind of divisibility relations popping out of Lagrange's theorem. Any doubts till this point?
No, sir.
Today the response is not what it was yesterday in the last meeting. I don't know what happened. Is this too slow or too fast?
No, sir, it's okay.
Yeah, let me know if it's too slow or too fast. We can move ahead. Next, conjugacy classes. Okay, so definition. Let G be a group and X be an element in G. The conjugacy class of X in G is the subset of all Y in G such that there exists a Z in G with Y equals Z X Z inverse. Is that fine?
Yes, sir.
Yeah. So what are some examples? So these kinds of questions really regarding conjugacy classes, these show up in the context of SN actually. So what is the conjugacy class of the permutation 1, 2, 3 in S3? What's the answer?
Two.
No, conjugacy class. I want a subset.
1, 2, 3, 1, 3, 2.
Yeah. So answer, the subset is 1, 2, 3 and 1, 3, 2. Why? Why is this the conjugacy class of 1, 2, 3?
For 1, 2, 3, we have identity element
Yeah.
satisfying y equal to. And for 1, 3, 2, we can take 1, 2.
Okay, let's see. So for 1, 2, 3, you're saying just take the identity. And for 1, 3, 2, you can take 1, 2. So how does one quickly compute this thing, this product? Have you revised the last lecture?
Yes, sir. We will operate the 1, 2 in the middle cycle.
Yes. So to compute a conjugation like this, you pick this element and you apply this. So think of this element as a function, apply that to each entry here. So by that idea, the answer should be instead of 1, I'll write this function applied to 1, which is 2. Instead of 2, I'll write this function applied to 2, which is 1 and 3. But as you know, this is the same as 1, 3, 2. Okay? Now, what is the conjugacy class of 1, 2 in S3? If you know the answer, don't spill it out. Does this work? So try to do this in your notebook. Try to compute all elements that are conjugate to 1, 2. I'll give you a minute or two. Can somebody tell me few elements of the conjugacy class? Those who don't know the answer. What's the obvious element inside the conjugacy class?
The identity.
1, 2 itself.
Identity is not an element because
So one symbolic.
So
yeah,
1, 2.
one symbol is not inside a conjugacy class of 1, 2. So you're saying this identity can be written as G1 to G inverse, right? But this is not true because this will imply multiplying by G on the right, you'll get G equals G times 1, 2. Multiplying by G inverse on the left, you'll get identity equals 1, 2, which is not true. So what this computation sees in general is the conjugacy class of the identity is a singleton set consisting of identity itself. Okay. Yeah, but as you said, 1, 2 is an obvious element. By taking Z to be identity, you can see that Y equals X is allowed. So 1, 2 is an element. Are there any others? How about this
Okay.
idea? The idea that I told you, computing conjugacy classes, sorry, computing conjugates inside Sn.
Sir, can we take 2, 1, or it is the same as 1, 2?
Is the same as 1, 2. So, so let's see. After 1, 2, we'll compute all the elements. So you want to do G times 1, 2 times G inverse, right? By this idea that we used over here, what is this equal to? This would be G applied to 1, then G applied to 2, right? Now, can you tell me more elements?
One comma 3.
Why?
We can take G equal to 1, 3, 2. So 1 will go to 3 and 2 will go to 1.
You're taking G to
G
be
equal to 1, 3, 2.
1, 3, 2. Then what will you get? G1 to G inverse is G applied to 1, so that's 3. Then G applied to 2, that's 1. So the answer is 1, 3. So 1, 3 is also an element. Are there any others?
Two, 3.
Yeah. How?
We can take G equal to 1, 2, 3.
Yeah. Taking G equals 1, 2, 3, we get G1 to G inverse equals, first you apply G to 1, so you'll get 2 in place of 1. Then you apply G to 2, you'll get 3 in place of 2. So that's 2, 3. Are there any others?
No, sir, because others are 3 cycles.
Yeah. So you note that using this formula, all conjugates of 1, 2 are 2 cycles. Is that clear?
Yes, sir.
Yeah, but is it clear to others?
Yes, sir.
Yeah. So if you want to compute conjugates, what is called as a cycle structure gets preserved. So conjugates of a 2 cycle are again 2 cycles. Now, how many 2 cycles are there in S3?
3.
There are 3 2 cycles. So all of them are conjugates of 1, 2, and no more can be can be a conjugate of 1, 2. So that completes the computation. So um, from this example, you can see that given a sigma in Sn, the conjugacy class of sigma in Sn is the set of all tau inside Sn with the same cycle type as that of sigma. Is this clear? So using this, tell me what is the conjugacy class of 1, 2, 3, 4 in S4? Does everybody understand what this theorem says? I need some responses from your side.
Yes, sir, understood.
So what's the answer here? Conjugacy class of 1, 2, 3, 4 in S4?
1, 3, 2, 4.
Mhm.
1, 3 a cycle and 2, 4 another cycle.
Yeah. So 1, 2, 3, 4.
1,
Then
3,
1,
2,
3,
4.
2, 4, and
1, 4, 2, 3.
okay, 1, 4, 2, 3. Is this clear? Now let me write down one thing. This is called as the class equation. I'll just write down this equation so that you at least get to see this once. Let G be a finite group then the idea is G can be written as a union of conjugacy classes, disjoint union of conjugacy classes. G can be written as a disjoint union of finitely many conjugacy classes and moreover you have this equation that the order of G, usually denoted by mod G, but okay, order of G is the same as sum of G colon Cg of G. Okay, I'll explain all of these. Representatives, where the sum runs over representatives little g in G of all conjugacy classes. Here CGG equals the set of all G prime in G such that G prime G prime inverse is the identity. This is called the centralizer. Okay, so this has various implications. This implies that the center of a P group is not equal to just the identity. So center means the set of all G in capital G such that conjugacy class of G equals singleton G. Okay, so you'll see this later in your life. You'll see how to use this later. Okay, next, a natural thing that shows up after conjugation is what is called as the concept of normal subgroups. So can somebody tell me what is a normal subgroup? What a normal subgroup is?
A subgroup H of a group G is to be normal subgroup of G
Mm-hmm.
for all X belongs to G and for all H belongs to H, XH
Mm-hmm.
X inverse belongs to H. Or we can simply say left coset is equal to right coset. Then it becomes a normal subgroup of G.
Right. So writing it in the first way, GH G inverse is contained in H for all G in capital G, H in capital H. So what does this mean? This means that the subgroup is a union of conjugacy classes of G. Okay, the subgroup H is a union of conjugacy classes of G. This is denoted by this symbol H triangle with a equality possibility and G. Okay, so what are some of the examples?
So GLNF is the normal subgroup of SLNF.
The other way around, right? SLN is a subgroup, normal subgroup. SLN is a normal subgroup of GLN. How to see this? Determinant is multiplicative. That's how you can see this. Okay. Then, any more examples?
AN is normal in SN.
Yeah. AN is a normal subgroup of SN. Any more?
Any subgroup of ZN is normal.
Yes. Any subgroup of Zn. So ZD is normal in Zn. Any others? So one interesting pair of a normal subgroup and a group is this. So if you take identity 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3, this is a normal subgroup of A4. Okay. Here you can see that this subgroup is a union of conjugacy classes, right? One is the conjugacy class of 1 is 1, and the conjugacy classes of all of these, the S4 conjugacy classes of these elements form this 3-element set. So by the same logic, A4 conjugates of this subgroup are also contained in this subgroup. Okay. Then UN, which appeared in the matrix groups, this is a normal subgroup of BN. Try to check all of these. I'm just giving you a list of pairs. Try to check whether this is true. Okay. And let me know in the next lecture if you have any doubts regarding any checks from this lecture. Then some non-examples. Sn minus 1 in general is not a subgroup of Sn. Is not a normal subgroup of Sn if n is at least 3. Okay. The copy of Sn minus 1 inside Sn that we chose is the one which fixes the nth element. That's not normal. Then Bn is not a normal subgroup of GLN. Okay. Then let me tell you some theorems. As you saw in Zn, the example of Zn, every subgroup of an abelian group is normal. Second, these are some theorems which you can memorize. These are really useful. If the index of H in G, I didn't really define this, but this is order of G divided by order of H. When G and H are finite groups, is 2, then H is a normal subgroup of G. Okay? I'm assuming G and H are finite groups over here. Although this fact doesn't require G to be finite. Then the third one is if G colon H, the index of H in G, is equal to the smallest prime dividing the order of G, then H is a normal subgroup of G. Okay? These are really useful facts which might show up later. So I think I'm out of time at this point. So let me ask you, do you have any doubts? Today the response seems to have died down a bit. What happened?
Yes, any doubt? Participants? Is there any doubt?
No, sir.
Sir, how can we show that the center group of a P group is not trivial?
Yeah, so it uses this class equation that I wrote down, this one. So let's see, how does one do that? So if order of G is a power of P, then the center of G is not just singleton identity. Okay, what's the proof? You write down the class equation. So order of G equals summation of these indices, Cg of little g, right? Now you can separate some of these indices out. So if you take G to be some element in the center, then you see that Cg of G is the whole of capital G, right? Every element commutes with G. G is in the center, means G commutes with every element, means every element commutes with G. So that says you can break this as order of ZG, break this into two sums, order of ZG and summation G not belonging to the center representatives G colon Cg of G, right? So now you note that order of G is divisible by P because that's what we assumed. And this index is also divisible by P. That's because this index is equal to order of G divided by order of Cg of G, right? Order of G divided by order of Cg of G. Order of G equals P power n, and Cg of G is a subgroup of capital G. Therefore, its order is of the form p power m for some m less than or equal to n. So this is again p power n minus m. But you know that note that this G is not in the center. Therefore, Cg of G cannot be whole of capital G. This means this n minus m that you see over here is at least 1. G is not in Zg implies m cannot be equal to n. Therefore, you can see here OG equals OZG plus summation G colon CG of G. Here P divides OG and P divides all of these indices. This means P also divides order of ZG, right?
Yes, sir.
Now, ZG definitely contains identity. Therefore, the order is at least 1, but since your prime divides the order of ZG, the order cannot be 1. It has to be bigger than 1. It has to be at least P.
Yes, sir.
So that means the center is not trivial. So this is a really important fact which will show up later in various inductive arguments. If you want to prove something for a P group, then you can use induction by breaking the group into its center and and some other part which is outside the center and apply induction. Okay?
Yes, sir.
Yeah. Any other doubts?
Sir, can you give the example of third properties of index of group?
Third property? The third theorem you're saying?
Yes,
This one?
the smallest prime was there something like.
Yeah. G colon H is smallest prime dividing order of G. Then H is normal inside G. So this will show up in the next talk, but let's see. So suppose order of G is 15. Okay, suppose order of G is 15. You factorize 15 into its prime factors, that's 3 times 5. Now, by Syllo's theorems, which will show up in the subsequent talks, you know that there exists a subgroup, I'll call it N, of G of order 5. Okay, this is by using some other theorem. There exists a subgroup N of G of order 5. Now, what's the index of N in G? This is 15 divided by 5, which is 3. So you can see that the index of N in G is the smallest prime dividing the order of G. So that means N is a normal subgroup of G. Okay?
Okay, sir.
Yeah. This is a really important fact which shows up a lot in questions related to Syllo subgroups. This even shows up in classification of groups. So if you, last time we did some classification, right? Groups of order 4, 6, 8. We saw that there are how many groups of order 4? How many non-isomorphic groups of order 4 are there?
Sir, 5 actually, partition of 4. P of 4 is 5, so there will be 5 non-isomorphic sub.
No.
So that's for abelian group actually.
No, but yeah. No, just some answer for 4. How many non-isomorphic groups are there of order 4? So what are some of the obvious ones? Yeah, somebody said 2. Yeah, there are 2 non-isomorphic groups of order 4. How about 6?
2.
Yeah, 2 again. How about 8? How many abelian ones are there of order 8?
3.
3. Those are
Z8, Z2 into Z4, Z2 into Z2 into Z2.
right. And how many non-abelian ones are there? Last time we saw at the end of last lecture.
2.
Yes. What are those?
D4 and Q8.
Yes, D4 and Q8. One is dihedral and the other one is some new group which is quaternions. So this result, the third theorem, which says that if you have a subgroup whose index in the group is equal to the smallest prime dividing the order of G, then H is normal. This helps you classify groups of a given order. So this, along with some Silo theorems, you'll be able to classify all groups of order P times Q where P and Q are primes. Okay. Yeah. Any more questions?
Sir,
Mm-hmm.
for non-isomorphic abelian group,
Mm-hmm.
when we have to find the order of the group, then we factorize the number and then we'll take the partition that is in the power, so that there will be that number of non-isomorphic group.
So what? Can you repeat? So start with a group, then
Sir, let's say you said how many non-isomorphic group of order 4.
yes,
So the prime factorization of 4 is 2 raised to the power 2.
yes.
So the power of 2 is 2.
Mm-hmm.
So we will take the partition of 2. So total number of partition of 2 will be the non-isomorphic group. Isn't the fact there exist?
No, because you see, right? This doesn't work for groups of order 4. I'm not so sure. I'm not sure about what fact you're saying.
Sir, it happens with similar with the order 8 actually. 2 raised to the power 3 and so partition
Mm-hmm.
of 3 is 3. So there will be 3 non-isomorphic.
You're saying abelian or non-abelian or all of them?
So for abelian.
Yeah. Abelian I'll need to think about, but you can work that out. Let me see. Yeah, turns out there's a different way of writing the classification. At least for P groups, let's see about the result that you're seeing. So suppose G is an abelian group. Let me tell you the general result first of order n. Then G is isomorphic to, you can write it as ZD1 cross ZD2 cross ZDR where you can arrange things so that D1 divides D2 divides dot 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 dr. Okay. So now if you start with a P group, suppose order of G is P power M, then to get these D1, D2, dr, you need a partition. Can you see how? So you first note that the product of all these D's is equal to P power M. So each one of these D's is a P power, and they are increasing, right? Therefore Di equals P power Mi with M1 less than or equal to M2 less than or equal to Mr, right? And their sum is equal to M. So that's how you get a partition. So maybe this is how you can see whatever result you said. Yeah. Any doubts? Any more?
Okay, we'll take the doubt in the next session, sir.
Sure, sure.
Yeah.
Okay.
Thank you so much, sir, for today's session.